Today we are going to be continuing with Chapter 7, which is Applications of Integration. Specifically, we are going to be talking about cross-sections, which goes along with the disk method. Specifically, we're going to be talking about cross-sections, which goes along with the disk method. So what we're going to be doing is we're going to be finding the volume of a solid using its cross-sections, which is an application of the disk method. The objective of this video is to be able to find the volume of a solid that has known cross-sections. So when we use the disk method, we found the area of one disk, really of one circle, or the volume of a cylinder, really, and we added up all of those disks. So we took these disks and we made them really, really skinny so that they were almost two-dimensional, found their volumes or areas, really, and added them all up. So the question is, what if we have a figure and its cross-sections aren't disks or washers? So it's a 3D figure that's maybe not the result of revolving something around an axis, and hence when I split it into pieces, those pieces aren't disks or washers. Now what that's called is it's called the cross-sections. So a disk or a washer is a cross-section of a figure. So we're going to be looking at figures that have cross-sections that are other shapes, not disks or washers. And what the idea is, we're going to find the area or the volume of one of those cross-sections, and then we're going to be adding them all up. So we're going to be looking at cross-sections such as squares, rectangles, triangles, semicircles, etc. So I think the best way to see this is just to look at an example. Okay, so this is the idea. Basically what you're going to be doing is you're going to be finding the volume of one cross-section and adding them all up. So if you look at this figure on the bottom left, you see that slice in tan? That's a cross-section. So in this case, it looks like it's maybe a trapezoid, maybe a rectangle. What you're going to be doing is you're going to be finding the area of that one cross-section, and then you're going to add up all of them. Same idea with the figure on the right. Figure on the right, it looks like the cross-section is a square. You're going to find the area of that one square and add them all up. So what's important to know is when you're taking a cross-section that is perpendicular to the x-axis, you want to use dx. When you're perpendicular to the y-axis, you're going to use dy. And then again, you're finding the area of the cross-section, and you're integrating from your starting point to your ending point. So again, it's probably easiest just to look at an example. So let's consider this example. It says, find the volume of the solid shown in the given figure. So that would be the figure on the bottom right. The base of the solid is the region bounded by the lines f of x equals 1 minus x over 2, g of x equals negative 1 plus x over 2, and x equals 0. The cross-sections that are perpendicular to the x-axis are equilateral triangles. Okay, so basically what we're saying is, looking at that figure on the left, that is the base of our figure. And then this little part right here is a cross-section. So we're going to be splitting this figure up into slices. Now each of those slices are three-dimensional, and two-dimensional really, they're equilateral triangles. So coming off of this, like coming out at you, are a bunch of equilateral triangles. And we're making them really, really skinny. So what we want to do is we want to add up the area of all of those equilateral triangles. So that's the figure that you're looking at on the right. This right here is the cross-section. It's one of those equilateral triangles. This part, the bottom of the equilateral triangle, is what falls on our region. Okay, so we're perpendicular to the x-axis, so we're going to integrate from x equals 0 to x equals 2. And then what we need to know is what is the area of all of these equilateral triangles. Because the idea is we're going to find the area of one equilateral triangle and add them all up. So the equilateral triangles, something like this. Okay, so the base of our equilateral triangle starts up here and ends down here. So the side length is 1 minus x over 2 minus negative 1 plus x over 2. So in this case, our side length is 2 minus x. So that's the side length of each side of our equilateral triangle. So it's just the distance from the point here to the point here. That will be the side length of the triangle. Now we need to know the area of the triangle. It would be helpful for you to know that the area of an equilateral triangle is the side squared times root 3 over 4. So in this case, our area is 2 minus x squared times root 3 all over 4. So then our volume of this figure, sorry, I know that I've run out of room. Our volume is going to be integrating from 0 to 2, since we're perpendicular to the x-axis. The area, like we said before, is all of that. So it's going to be 2 minus x squared times root 3 over 4, all times dx. That will be the whole volume of the figure. And again, the idea here is that we're finding the area of one equilateral triangle, which is a cross section, and we're adding them all up. So all of the equilateral triangles from 0 to 2. The dx means to make them really, really skinny. Really, really skinny equilateral triangles, and then adding them all up. So let's look at one more example. This example says let R be the region bounded by the graphs of x equals y squared and x equals 9. Find the volume of the solid that has R as its base, and every cross section is a rectangle of height 2 that is perpendicular to the x-axis. Okay, so this is our figure here that you see on the right. And what all of this is saying is that when we split the figure up, so we take a little cross section, that cross section is always a rectangle that has a height of 2. So we're splitting the figure up into a whole bunch of different rectangles that have a height of 2. Because we are perpendicular to the x-axis, this is going to be in terms of x, we are integrating from x equals 0 to x equals 9, and then we need the area of each of those cross sections. Well, the cross sections are all rectangles. The height of each rectangle is 2. We're told that here. And then the base is 2 root x. Now, the way we get that is we have this point up here. That's x over root x. This one is x and negative root x. So then to get the base of the rectangle, it's where we start up here. So that's root x minus where we end down here, which is negative root x. When you subtract those, you get this 2 root x. So this is how we would express our volume then. This is saying start at x equals 0, go up to x equals 9. This is the area of each rectangle. And then that's saying make the rectangles really, really skinny. So we have these rectangles that are coming out at us. We're finding the area of each one and then adding them all up. So we're using the integral as an accumulation process. Make these cross sections, these rectangles really skinny, add them all up. Okay, and then we have one more. Find the volume that is created by cross sections, which are equilateral triangles, perpendicular to the y-axis, on a base, which is a circle of radius 4. Okay, so this figure all the way to the right is the base of our figure. And then what's happening, this three-dimensional figure that we have, has a whole bunch of equilateral triangles that are coming off of it. And so we're trying to find the volume of that figure. So our area idea, this time we are perpendicular to the y-axis, which means everything has to be in terms of y. Down here, y is negative 4. Up here, y is positive 4. So we're integrating from negative 4 to positive 4. And then we need to know the area of each triangle. And they're equilateral triangles. So remember that from before, the area of an equilateral triangle is the side squared root 3 over 4. So we need to know one side. Now, this is the equation of our circle. So we solve for x. This, then, is right here. It's that part. So it's only half of the base of the triangle. So this, then, is the whole base of the triangle. I just multiplied by 2 so that I got the whole base. The area of the triangle is set up here, and it simplifies to that. So again, the idea here is we have this base that's a circle. Our three-dimensional figure is when we build a whole bunch of equilateral triangles off of the circle, like jumping out at us. So we found the area now of one such triangle. We want to add all of them up as an accumulation to find the volume of the figure that's created. So then this is what we end up with. We are integrating from y equals -4 to y equals +4. And then this is the area of our equilateral triangles. The dy just means make them really, really skinny and add them all up. So if you do all the integration by hand, this is the volume that you end up with. So again, in this video, we talked about finding the volume of a solid that has known cross sections. So the idea in the video is you're going to be given the base of the figure, and you're going to be given the cross sections. And cross sections are just slices of the figure. So what you're doing is you're finding the area of each cross section, so an equilateral triangle or a rectangle, and you're adding them all up for the whole figure to find the volume of the whole three-dimensional figure. If you have any questions, please ask.